Aeroplanes and women's breasts, while both uplifting, would seem to have little in common, although the mathematicians at the University of Auckland have made a unique connection. Engineering expertise once lavished on a plane's wing is now being used in breast imaging to help with medical treatments. And here to tell us a bit more about this unique synergy is mathematician Martyn Nash. Hi Martyn.
Hi.
Thanks for talking to us today. Now, first off, what sort of medical treatments would we be talking about, and how would breast imaging be helpful?
So what we're interested in doing is detecting breast cancer and detecting it early. So the standard techniques are kind of X-ray mammography, where they compress the breast largely between two plates, very high levels of compression, and that can be followed by other sorts of imaging techniques like magnetic resonance imaging and ultrasound imaging to follow up and determine whether or not what you see in an X-ray mammogram is actually a cancer or not. The problem is that the clinicians, whilst they're very good at this, they need to kind of mentally draw pictures to map information from one compressed state of the breast to the breast in a pendulously state position, someone lying prone on their stomach where the breast is not compressed. For ultrasound, the person is lying on their back and the breast is fairly flat against the chest. And they have to take information from each of these states and kind of draw a mental picture as to where the region of interest, potentially a tumour, has moved between these two states. So that's pretty tough, and what we can do is use the laws of physics to do that. So the idea is the breast is a soft body which behaves like other soft bodies, rubbers and things like that, deforms due to the effects of gravity, for instance, or compression in the case of mammography. And we can use the laws of physics to determine how the breast will change shape, predict how it changes shape. And the reason we want to do that is to be able to map this information together, to bring together information from all of these different imaging modalities into one common framework.
So that's what you're basically doing, you're integrating all that information
Yep.
into one. So would that mean that every patient would end up with their own personalised model that the clinicians could then work with?
That's right, yeah. So the approach is to develop a three-dimensional personalised model, not just the geometry, but also the stiffness, so the mechanical properties of that particular person's breast, because we know that the fat, the fibroglandular tissue, the skin, the muscle, they all behave differently when they are subject to the laws of physics. Mm-hmm. Some are more stiff, some are more soft. Some have directional behaviour, so the skin has got, it stretches, it's stiff in one direction and soft in another direction. It stretches differently in these different directions. And so we need to bring all of that information together using this mathematical modelling framework to be able to determine how or predict how the breast will change shape due to these external loading conditions.
So first stage is mathematical modelling, and then from there you try and make something physical.
No, we don't actually try to make anything physical.
Oh, okay.
What we're trying to do is to take the existing imaging information, so this stuff is being measured by the X-ray mammography machine, the magnetic resonance imaging machine, and we're trying to encapsulate that in a computer modelling framework. So we're trying to visualise that person's breast, plus all of the internal information, all of the fat, the fibroglandular tissue, and importantly the tumour information. Where does that tumour move when you compress the breast? Where does that tumour move when you put the patient lying on their back? That way we can bring that information together into one common framework and help with detection.
Why is it important to know where it moves?
So, for example, magnetic resonance imaging is good at high tissue contrast, so it's good at looking at, say for instance, regions of increased blood flow, but you cannot see that under X-ray mammography. X-rays are very good at finding very dense regions of tissue, so cancerous tissues or calcifications, which can be early signs of cancer. And the idea is, for instance, if you can map regions of high calcification with regions of increased blood flow, if they co-locate, then the risk of breast cancer is that much greater. But each of these techniques only picks up half of the story in that case.
Okay, so is it also helpful in terms of basically taking biopsies and all that kind of stuff?
Sure, yeah. So if something is spotted in terms of the X-ray mammogram, typically what they'll do is they'll take them for what they call second look ultrasound. So they'll go from the compressed state to lying on their back. Looking at an ultrasound probe, they want to find where that that suspicious lesion is, the potential cancer, and then they'll look to stick in a hook wire and potentially a biopsy needle. The problem is it can take anywhere between half an hour to an hour sometimes to find some of the smaller cancers, some of the things that potential cancers. Some of the things you see in the X-ray mammograms, they have to actually be able to find it with the ultrasound probe. And so they're kind of fishing around trying to find that lesion which looks different under the ultrasound imaging. What we can do with these techniques is show them where to look, help them reduce that time to finding it. Sometimes they can't find it.
And you'd show them by looking at a computer screen and going,
that's right. Well, we can provide them with sort of three-dimensional feedback in terms of where we believe that tumour has moved to, so where they should be putting their probe, where should they be looking for that potential lesion. And if you've ever seen anything like an X-ray mammogram or an ultrasound, it really is looking for a snowball in a snowstorm. Mm-hmm. It's incredibly difficult to find some of these smaller cancers, potentially, particularly in women with more dense breasts. Mm-hmm. It's very difficult to spot some of these cancers for very trained radiologists.
So that's for younger women who came in, that would be the case, is it?
Not just for younger women, but that's particularly the case with dense breasts. Yeah. Younger women typically have more dense breasts.
Okay. So what prompted the aerodynamically engineering approach to this imaging?
So it's a standard engineering approach in the sense that we use numerical methods which were designed in the 1950s to model aircraft wings, which is your start to this segment. We're using what we call finite element methods. These are highly mathematical, kind of numerical methods to simulate the kind of mechanical situation. It's just a mechanical engineering problem in a sense. We're determining how these objects change shape due to external loads, just physics. But the difference with the biological tissues is that you get very, very large deformations, very, very large changes in shape. So that brings into account all sorts of non-linearities into the system. So whereas the finite element method that was designed for aircraft wings, relatively small deformations take place, relatively linear sorts of systems. We're looking at highly non-linear systems, very large deformations, very non-linear elastic behaviour, and that's the sort of challenges with applying the standard engineering techniques into the biological world. And we've done this for a range of different organs. So I started out doing a PhD in mechanics of the heart. I was looking at how the heart deforms as a mechanical pump. How does it develop pressure? How do the particular regions in the walls of the ventricles change their shape? And it's exactly the same engineering techniques applied to this different biological situation, compression and gravity loading of the breast.
So how long have you been working on the project for?
So we started with a graduate student here in Auckland, Vijay Rajagopal. So Paul Nielsen and myself co-supervised Vijay. He started in 2003, and now he's a co-leader of the team with us. We've had significant funding from the government to grow our team to about 8 or 9 people now. So yeah, we've been going for about 7 years, I guess. And
at what stage do you think you are in the project in terms of getting to your ultimate goal?
So we started off with very, very simple applications, just in the laboratory situation. So looking at soft gels and compressing gels and cantilevered beams in terms of deflecting gels under gravity. We've then moved into doing our own MRI on volunteers. So looking at putting volunteers in different positions within the magnetic resonance imaging machine, on their tummies, on their backs, on their sides, and looking at how the breast changed shapes, putting them in water to take away some of the effects of gravity, so neutral buoyancy imaging. So we're trying to put the breast under different loading situations, I guess, to put it in different shapes and see if we can predict and learn about how to tune our models to those individuals. So we did that ourselves probably in about 2004, 2005 on volunteers, and now we've established good links with Auckland Hospital, and we have clinicians Anthony Doyle and Wayne Jones in the hospital who are providing us with data to apply this to the clinical situation. So we have X-ray data from patients and we have MRI data from patients to help us validate our models.
How soon do you think you might get to the point where they actually use this?
So we're providing information back retrospectively on patients, and so it's not actually helping patients today. We've got a few challenges that we need to overcome. One is how fast can we do it? We've put no real effort at this stage in terms of making it real time or anything like that, because that for us is a sort of a final a final way of getting things going. Right now, what we're trying to do is concentrate on the accuracy. How well can we predict things? And our models are able to predict deformations to within 10 millimetres or so. It's not quite good enough. I think for the clinical situation, we need to be able to predict motion of tumours to within about 5 millimetres so that they can act on that appropriately. But in terms of getting information back to clinicians to help them with detection, our time frame is within the next 3 or 4 years. We would like to have our first kind of product to be able for them to try out in a clinical setting. Yeah. I mean, we're working with them interactively. They're helping us sort of set up and telling us what sort of information they need, but all this is based on sort of retrospective studies at this stage.
Would it have any other applications like breast reconstruction or anything like that?
Yeah, we've attempted a few different projects. So looking at breast augmentation, for instance, breast reconstruction, reconstructive surgery, where people have had mastectomy. One of the breasts has been cut away to reduce the risk of cancer, obviously. And looking at designing prosthetic devices. We're not really pushing those boundaries at the moment. We've had a few pilot projects in those arenas, but certainly there are opportunities to look at things like that. Reconstructive surgery, augmentation surgery, and so on. Reduction surgery for larger breasted women. Sure.
Oh, fantastic. Well, I have to say I'll never look at a plane's wing quite the same. So anyway, Martyn, thanks very much for talking to us today.
Great.